another interface problem. So is everything okay so far? Any question or? This book, this note will be published in a book as a chapter. It's published by the French Mathematical Society. I forgot the title, but anyway. So this new interface problem is we have a core with conductivity 1, the dielectric constant 1, and shell, which is a negative dielectric constant of -1 plus I delta. And so this delta is a lossy parameter. It's a attenuation kind of. Now, so this anomalous localized resonance was first found by these people, Nikrovich, McFadden, and Milton in '94. And this relation to the invisibility cloaking was first demonstrated by this Milton and Nikrovich, and this you just saw the video clip. This video clip is famous. It's downloaded more than 20,000 times or something like that. This is a very so Starship Enterprise disappears. So and the Pandry also did some work. It has something to do with the superlens, and this is a figure. So this is a source, and you see there's some the kind of the mirror image of these sources. This is a superlens effect. So he observed this kind of phenomena. So basically, what's happening is energy concentrate on the interfaces. Here is a interface, and here is another interface, and so on. Okay. So what is the problem? Problem is given a function f. This is a source, and consider the following: the elliptic, not elliptic, the electric problem. So this is a structure, 1 minus 1 plus I delta and 1. So even as a PDE, this is you can expect something strange happens, really. So this is 1 and minus 1 I delta and 1. So here, if delta is 0, it's negative. So we are completely out of the elliptic regime. Okay. So completely out of the elliptic regime. So something strange should happen. Okay. So we consider this problem, and then let this integral. This is the energy. So this kind of the electromagnetic energy, and the imaginary part of that is just this one, and this is E delta. So E delta is the imaginary part of the, electromagnetic energy. And the problem of cloaking by anomalous, CALR, cloaking by anomalous localized resonance, is identify the source such that E delta become arbitrarily large as delta goes to 0, and this division goes to 0 as outside some radius. So E delta is electromagnetic power produced by source. So one implies that electromagnetic field this is how they explain this cloaking phenomena. E delta energy become arbitrarily large, so which is unphysical. I don't know what that means, but they said that. And then, so if we divide this factor by this quantity, then the energy become the 1. But this one, because of this condition, this one becomes small, so the source is cloaked. This is how they explain this thing. Now, then, so remember that we want to characterize all these F such that this electromagnetic energy become large. Okay? We want to characterize all these sources. Okay. Again, this is interface problem. So on the core, on the boundary of core, this is the continuity of the flux, and this is the continuity of flux on the shell, right? Now, if I take a Newtonian potential of F, so Newtonian potential is like that, then F satisfies Newtonian potential. I mean, if you take the gradient, not gradient, the Laplacian, then it is F. So this F satisfies this. So solution can be written as this. Okay. Single layer potential on the boundary of the core and the single layer potential of the boundary of the shell. Now, this is again this interface conditions. This condition can be written like this, and the Z delta is this one, and as I said, as delta goes to 0, this one goes to 0, so it goes to the essential singularity of the Poincaré-Neumann operator. So this is our Poincaré-Neumann operator, which comes from this integral equations, and this Neumann-Poincaré operator. So our integral equation can be written like that. Okay. And again, Z delta goes to 0 as delta goes to 0. So we are approaching to the essential singularity of this operator. So it's very difficult to deal with. So the way we choose to deal with this problem is spectral analysis. So these are proved in this paper. It appeared in ALMA this year. So we proved that this Neumann-Poincaré operator the spectrum of this operator lies in between -1/2 and 1/2, like CALR's results, and the adjoint is given by this, and the single layer potential is defined by this. This is a self-adjoint. And as before, so this quantity is inner product in the space, and the Calderon's identity holds. So it's the procedure is completely equivalent. So because these ones are the inner product, and the K star is self-adjoint in this with respect to this inner product, so we have the spectral decomposition. Okay. This is the spectral decomposition, and so the solution of this integral equation. Solution of this integral equation is given by this. Now we plug in this solution into the single layer potential. Then this quantity is the E delta, the electromagnetic energy. So we want to characterize the source F such that this guy goes to infinity as delta goes to 0. Okay. Now, so in general, I don't think it's possible to find the eigenvalues, eigenvectors for the general shape. But fortunately, for the circular structures, we can compute. So single layer potential looks like this. And so if the omega is a disk with radius RE, and the D core is a disk of radius Ri, and the low is like defined by this, then eigenvalue of the Neumann-Poincaré operator is given by this. So low is less than 1, and these are all powers. So this Neumann-Poincaré operator, the spectrum goes to 0 exponentially fast. Okay. And we can compute the eigenfunctions too. Now we plug in this formula into this formula, then the critical radius. So as you saw from the video clip, there is a critical radius, right? And the critical radius is given by this. Okay, and if the source function is supported outside, then energy is bounded regardless of delta. And if the source function is supported outside, then we can recover source. And if the source function is supported inside the critical radius, then in general, lim sub of the energy become large, goes to infinity. And in addition to this, suppose the Fourier coefficients of f satisfy this gap condition. Gap condition is it's not so easy to understand this gap condition, but the gap is the non-zero coefficient of the Fourier coefficients of the f appears. Appears regularly. Then this cloaking happens. Okay, so this is a characterization of this. There is one interesting problem. Actually, this problem was also, we discussed with the Bob Cohn and these people. Is there any source which actually this lim sub is infinity, not the limit? Lim sub is infinity means, and not the limit. It means that the energy become, for some delta energy is very large and some delta energy is small, large, small. Is there any source that happens? We don't have example. So it should not satisfy this condition, this source. But this gap condition is mild. So to construct the source which does not satisfy this gap condition is difficult because it is quite mild. So for example, dipole source, gap condition is satisfied. So the energy blows up. And for the quadrupole source, it's it satisfies gap condition. And this result also, these people, Kohn, Lu, Weinstein, and these people use variational principle, but basically it's the same method as ours, extend a little bit. Then what happens in 3D? 3 dimensions. 3 dimensions. Let me skip this. In 3 dimensions, this is spherical harmonics, and we can calculate the single layer potential of spherical harmonics, and then it is like this. Okay. And so the eigenvalue looks like this. It looks ugly, but what is important is that it's only decaying, approaching to 0, but it's just like a 1 over n, asymptotically, right? And because of this slow convergence of this eigenvalue, in 3 dimensions, never occurs. Energy is always finite. So our conjecture is for any structure, there is no structure in 3D where the anomalous, cloaking by the anomalous localized resonance occurs. At the beginning, I said that this 1 over n, Ball has the fastest convergence rate, and it is related to this question. But this is not the end of the story in 3D. here we constructed 1 minus 1 plus I delta 1. Then in 3 dimensions, anomalous localized resonance does not occur. Okay? But instead of the 1 minus 1 plus I delta, we designed this one. This is anisotropic and non-constant. We designed this, then anomalous localized resonance occurs. We proved that. And how we got this? This is looks strange. How we got this? So this is a folded. It's called the folded geometry. So this core. So if you look at this, this is strange, right? Core is here, and the shell is not outside. The shell is inside, right? And so, if you look at this from this side, core is outside and shell is inside, and it folded, unfolded. Then, if you look at this side, core is inside, shell is outside, and the matrix, right? Now, here we set here the conductivity, the electric constant is 1, and here minus 1 plus I delta and 1, and the push forward. That push forward is this one. Okay, and for this one, anomalous localized resonance occurs. Actually, this is not the unfolding map. Is not the our own idea. This was introduced by this person, Leonhardt. He's a physicist. He's changing lights using conformal mappings. So this problem I just discussed. Okay, so is there any structure, any source where the anomalous resonance, I mean the energy become fluctuating? And maybe this is for general shapes, it looks like it's a really hard problem. Okay, but for the confocal ellipses, we were able to compute the radius. So this is a recent paper, and also this Daewon Chung is writing a paper on this multiple coating. Okay? To see the interaction between the structures. Okay. Let me tell you, maybe we just discussed. Let me tell you one problem which seems challenging and very interesting. Okay. So, these plasmonic structures, they use in physics. They use, I mean, in physics and engineering, they use this plasmonic structure to make the composites, nanocomposites. But the question is this. I have core, and I coat it by plasmonic structure. So this is 1 and minus 1 plus I delta. And so because this is composite, we have another one. So 1 minus 1 plus I delta. And this one has critical radius, right? Critical radius where and this one has critical radius, right? Question is, what happened here? So resonance occurs, and resonance occurs. What's going on here? This is not just the energy, it's a local analysis of the behavior of the field. It looks like something even strange is happening there, I expect. And this question is related to the next topic of my talk, stress concentration. Okay. This is also related to the Poincaré Neumann operator, okay, interface problem. So stress concentration is this. Suppose, so I have a composite, and some inclusions are very close to each other. Okay, some inclusions are very close to each other. Then if the inclusions are close to each other, then in between these inclusions, stress occurs. Okay? And now, we want to analyze the stress quantitatively. So estimate the stress. And what is the stress? Stress is just the gradient of the solution. Okay? So we want to estimate the gradient of the solution when two inclusions are very close to each other. So it sounds like a completely different problem, but it is related by the so this is kind of the stress analysis problem, right? This is the two inclusions, but they are not close here. Just the critical radius, as I said, close. Okay? So, in composite, which consists of inclusions and matrix, the matrix is the background medium. Some inclusions located very close or even touching to each other. Touching case is if it touches, the potential is the same, so stress does not occur. Okay? So touching case is different. If conductivity inclusion stays away, so the situation is this. I have inclusion, and conductivity is K, 1, see? If K is finite, so stay away from 0 or stay away from infinity, then stress is bounded regardless of distance between inclusions. This is well known, the theorem of Bonatier-Vogelius. They treated the circular case, and the Lee-Vogelius, this is for general shape, and Lee and Nirenberg extended it to the system. Okay. But there are some, in engineering literature, there is some evidence, numerical evidence, that the gradient of U may blow up as distance tends to 0. Okay. This is a result of the Joe CALR and the Budiansky career, and these people computed it. Okay, so this is composite. Maybe I should have to write this. I have a composite with lots of inclusion here. Okay. Now there is another way of the looking at this the stress. I mean global stress. But the global stress, in order to analyze global stress, you need a different kind of model. Okay, this is completely different story. Maybe his name is Burley. I cannot. Maybe I wrote this. Anyway, there is a way. The different kind of model developed by these people. But what we are interested in is local stress. Okay? But if you look at this, local stress occurs only in between these two. Okay? So instead of looking at the whole picture, we just look at the two inclusions. Just the two inclusions. Okay? Now, so the conductivity distribution is K, and 1 outside. And we consider this conductivity equation. Okay. This problem can be understood as a conductivity problem or anti-plane elasticity problem in 2 dimensions. So problem is this. Estimate size of the gradient of U in terms of distance between these two inclusions. Okay, when K is 0 or infinity. K is 0 means, K being 0 means that this inclusion is insulated. And K being infinite means it is a perfect conductor or very hard, very stiff inclusions. Okay. So if the K is infinity, then it is a perfect conductor. So it is conducting immediately. So inside the potential must be constant. So it is a constant on the boundary. And this constant is determined by these conditions. If the K is 0, it is insulating. Okay? Insulating means the no flux goes into the inclusion. Okay. Now, in this case, we want to estimate gradient of U in terms of delta. Okay. So, actually, we started in this paper. We started looking at this problem when inclusions are circular. Okay. In 2005, this is a mass annulus and then so on. It turns out that the blow-up rate is delta to the minus 1/2. So the estimate is like this. It blows up as delta goes to 0. But C may depend on H. But we, Yun and these people. So this is a circular case, and this is a general convex case, 2D. And the 3D, surprisingly, the blow-up rate is delta log delta, 1 over delta log delta. It's a surprising result. And this was proved by Yan Lee and his students. And this is general convex domains. And this is a spherical case, Lim and Yun. Lim is a professor here, Lim Mi-kyung. And there is a physicist, Lechner, also got this. And the K is infinity, K is 0. In 2D, there is a harmonic conjugate. So if we understand the perfectly conducting case, then we completely understand the insulating case. But there is one big open problem. Nobody knows what happens in 3D. So I can write down this problem. Estimate gradient of U when K equal to 0 in 3D. This is completely open. Even we don't know whether it blows up or not. There is a possibility that it does not blow up. Okay. So motivation of this analysis is estimates of stress in composite when the grains are very close to each other. And this problem was actually raised by the Babushka. And this Vogelius was student of Babushka, and so he got this problem, and he worked on this. And in 3 dimensions, it is a computation of the electromagnetic field. If the 2 inclusions are very close, maybe you know that it's hard to compute the gradient of U. So now okay, solution to this problem is as we discussed before, solution to this problem can be written as H is the background potential, and the single layer potential and another single layer potentials. Okay. Then U is constant on the boundary D1 and the D2. That's the perfectly conducting case. Can be written in this form. This condition can be written in this form. So again, we have Poincaré Neumann operator. This one, and this one, and this one. Okay. So here we have the Neumann-Poincaré operator, and our system of equation is this one. Okay. So maybe, okay, I can finish. We don't have to go for another class. I mean, just let's do about 30 minutes more. So should I pay you back then? Okay. We want to solve this. Where is the difficulty? It looks like it is a very simple integral equation to solve. But the difficulty is this one. Eigenvalue, if the 2 inclusions are very close to each other, then this is proved by Bonatier and the Tricky. They proved that the eigenvalue accumulates to 1/2. Okay. You see, we want to solve this one, but this one has a very small eigenvalues. So, what does that mean? The condition number is pretty bad, right? We cannot easily solve this problem. Right? Okay. So, here is what we did. This is recent results. Okay. So, this, if there are 2 inclusions, then the multiplicity of the eigenvalue 1/2 of this Neumann-Poincaré operator is 2. If there are n components, then the multiplicity is n. Okay? So we choose eigenfunctions such that this satisfies. Then substitute these functions into the single layer potentials. Then, as a linear combination of these eigenfunctions, we can make one eigenfunction such that the integral of G1, the first component is 1, and the integral of the second component is -1. And define these eigenfunctions, using these eigenfunctions, define this function Q, we call it the singular function. And this Q satisfies, is harmonic outside, and constant on the boundary, and integral is 1 because of this property, 1 and -1. And this is eigenfunction corresponding to 1/2. Okay. What kind of function is this? So constant, but these constants are not determined. And the integral of the flux is 1 and minus 1. Okay? And this function, this singular function is, there is an amazing formula. This formula was found by Yun. Okay. Suppose, okay, here are two disks. This is two disks. So you reflect it with respect to, first you reflect everything with respect to this disk, and then reflect back by this disk. Then there is a fixed point. There is a single fixed point, and there is another fixed point by the repeated, the fixed point by the repeated reflections. Okay? You can easily see that there is two fixed points. Then, what is this? This ratio from this point and I mean, this distance and this distance, the ratio is constant. This is a Greek, I mean, a very old observation by the Apollinaires. It means that this one divided by this one is constant. So log of this is constant. But this function and this functions are harmonic functions. And actually this is the function, singular function. What is good? What is good about this Q? This is a 3 dimensions. Just let me skip this. Okay. Our solution U is here. Our solution U is here. And I define the constant like this. This is a potential difference and the potential difference of Q. And subtract this. Then what happened? R is the regular function R satisfies. It is a constant, and the constants are the same. This constant and this function is also constant on the boundary of D1 and D2, but these two constants are the same. So constant, there is no gap, right? No jump. So the gradient does not blow up. You can easily see that the gradient of this guy is bounded. So the stress of this one is completely characterized by stress of this guy. The gradient of U, singular behavior of the gradient of U is completely characterized by singular behavior of gradient of Q. Right? Okay. And if it is a circular, then this we can compute this constant. You can compute this constant, and this constant turns out to be this one. So we call it the stress concentration factor. So solution U is given by this constant and the 1 over 2 pi and log, difference of log, and some function B, which is gradient of B is bounded. So singular behavior of this function is completely characterized this way. And one good thing about this is that, so how do we compute then? How do we compute the gradient of U? So we don't have to compute anything about this. So we subtract this and then compute the gradient of B using regular mesh. You don't have to you don't have to make a fine mesh to compute. It's just a irregular mesh. Okay, this is an insulating case, so it's just the harmonic conjugates. So this is a computational result. Let me emphasize that this is the computation is done using regular mesh. Okay? And this is insulating case computation, and you see that there is a sharp gradient there. What happens if the if what happened, so understanding this singular function is crucial in understanding the stress concentration. And so we ask ourselves, how do we compute the singular function when domain is just convex, strictly convex? And it turns out that this is convex domain. Then you can put the oscillating circles, and the oscillating circles has a fixed point, and you define the log x minus p1 minus log x minus p2. So it's a singular function for the two circular case. And then then this singular function corresponding to this red curve is almost the same as, approximately the same as singular function corresponding to two circular cases. Okay, so stress, the solution can be written like a singular function corresponding to the two disk and times the stress concentration factor. And the stress concentration factor this is curvature, and this is an eigenfunction of the Neumann-Poincaré operator, and H is background potential. Okay. But there is of course, it's difficult to find the eigenfunction of the Neumann-Poincaré operator. There is a difference. So, we are writing a paper about how to compute this guy. There is an easy way to compute this guy. So discussion is this now this problem is pretty well known. In three-dimensional insulating case, even just the two spheres, two balls, yeah? Whether it. Let me tell you why. There is a possibility that no blow up occurs. Circular case. So why it blows up? Why it blows up? Suppose the field is coming like that, but these are insulating. No flux goes in there. Okay, then field coming like that, then it squeeze here. So it becomes very, very large here, right? Make sense? But suppose there is a 3 dimension. Field goes in, then it goes around. There are enough space for the field goes in. So because of that, there is a possibility. My guess is that there's no blow up, but I don't know how to prove it. I don't know how to prove it. So this problem is pretty well known. Another one is so we were dealing with this is also a pretty well known problem. We are dealing with the case when k is infinity and 0. But what is the dependency? There is nothing like a perfect conductor. So it is very close to perfect conductor. So which means the k is very large or k is very small. Then what is the dependency on k in this blow up estimates? Okay. And we also proved that this is also an interesting problem for the composite theory. Suppose this radius is r, and this radius is r, and this distance is epsilon, or delta, I wrote. If the delta is comparable to r, then blow up does not occur. Okay? 2D case, yes, yeah, 2D case. I think this is true for the 3D case, also for the general shape. Okay. So diameter is comparable to the distance, then no blobs. This is important for the nano composites. Right? Nano is very small, but they are very close to each other. Right? And I don't know how. We only proved it for the circular case, right? Two-dimensional circular case. And there are lots of problems in this. Okay. For example, so isotropic elasticity. What is the blob rate? Elasticity case. I heard from Yan that they made some progress on this problem, but other than that, there's no results about this. And also, very challenging problem and very important in application, the stress estimation for the heat equation. Okay? So heat is concentrating, so estimate this heat equation. Also, this noise. Noise means acoustic problems, Helmholtz equations. So this in this business, there are lots of problems to be considered. So the young people like you may come in and investigate, study these problems. Very interesting problems. These. Okay. Thank you very much for your attention.